Hello and welcome to part 2 of graphs where we're going to do some example problems. If you want to find the video with all the concepts, look in the description box where we'll have a link for part 1. Okay, let's get on with it. Example number 1. The graph below is a position versus time graph for a bicycle traveling on a long straight road. Look at only the first 40 seconds. Describe the motion of the object during this time, i.e. constant or variable, going away or towards the origin, etc. Okay, so this is the first 40 seconds of our motion, and we need to make sure to check our axes and know what type of graph this is. And this is a position time graph. So make sure you always do that so that you don't get confused and think, oh, is this a velocity time graph, etc. Now, this line is a linear line, which means that our object is moving, or our bicycle is moving at a constant speed. And it looks like it's going away from the origin because the position of this object is getting higher and higher away from zero in the positive direction. So specifically, it's going away from the origin in the positive direction. Okay, part B. What is the velocity of the bicycle during the first 40 seconds? Show calculation. So remember, our velocity on a position time graph or a displacement time graph is always going to be the slope of the graph. So for the first 40 seconds, our slope or velocity is going to be change in y over change in x. So over here, 25 meters minus 5 meters on our y-axis over 40 seconds minus 0 seconds for our x-axis. And that gives us 0.5 meters per second. So during the first 40 seconds, our bike is moving 0.5 meters per second to the right. Part C. What happened at the 40-second mark? Be specific. Okay, so why don't we draw out maybe a little picture of what happened? So our object starts at the position of 5 meters, let's say around here, and then at 40 seconds, it's at the position of 25 meters. So let's say that's over here. Now, for the first 40 seconds, the object was moving from this 5-meter mark towards this 25-meter mark, like so. But then, if we look after 40 seconds, the object is getting closer to zero. It's turning back around. So this object basically turned around and started going back this way. So precisely at 40 seconds, looks like our object turned around. And we can see that in the graph too, because first we have a positive slope here, and then we have a negative slope over here. So our object changed direction. Now, if you remember, when an object turns around, what happens to its velocity momentarily? It comes to rest. So at this 40-second mark right here, the object's velocity was momentarily at 0 meters per second. Now, in real life, this graph is actually not possible. It's not possible to go from 0.5 meters per second instantaneously to 0 meters per second over here. In real life, the graph might look something like this. We start with this 0.5 meters per second, and then maybe over a course of 1 second or 1.5 seconds, we undergo a brief period of negative acceleration, wherein the object slows down its velocity from 0.5 meters per second to 0 meters per second. That's what would happen in real life. You wouldn't have an object instantaneously go from 0.5 meters per second to 0 meters per second. Okay, part D. Describe the motion of the bicycle during the last 20 seconds of the trip, from 40 seconds to 60 seconds. Okay, so that's this time frame over here. Now, our object is still moving at a constant speed because this graph is still linear. The only difference is that now it's moving in the negative direction. How do we know this? Well, that's because it's starting from some positive position, 25 meters, and it's moving closer and closer to the origin. So it's not getting more positive, the position is getting more negative. Now, another difference from the first 40 seconds of the trip is the speed of our bicycle. Over here in this section, you can see that the slope of our graph is a little more steeper than the first 40 seconds. Why is this? Because it's covering more position over a shorter period of time. In fact, in the last 20 seconds, the object covered the same amount of distance that it did in the first 40 seconds, but over a shorter period of time. Therefore, it traveled at a faster speed. There we go. Oh, sorry, the text is a little bit blocked. The bike is going at a constant speed that is faster than before. It is traveling towards the origin, or with a negative velocity. Part E. What was the velocity of the bicycle during these last 20 seconds? and show the calculation. Well, we know how to do this. We just take the slope of the line from 40 to 60 seconds over here. Now, the slope is going to be the change in y over change in x, but remember, the change in y is the final y value minus the initial y value. So we're not going to put 25 minus 5 on top. We're going to put 5 minus 25, and then our change in x is going to be 60 minus 40, and this leads us to negative 1 meters per second. So the velocity of our bicycle during these last 20 seconds is negative 1 meters per second. And finally, part F, when during the trip does the bicycle have a positive velocity and when does it have a negative one? So we know how to do this. All we do is look at the slope of the graph. From 0 to 40 seconds, our slope is a forward slash like this. That is a positive slope, so it has positive velocity from 0 to 40 seconds. From 40 to 60 seconds, our graph is a backward slash or a negative slope. So our bicycle has negative velocity from 40 to 60 seconds. Okay, example number 2, part A. Is one object moving at a greater speed, i.e. moving faster than the other? If so, which one is faster and when? Explain. So let's look at this graph over here and make sure you know what type of graph you're dealing with always. This is a position time graph. We know that for position or displacement time graphs, the slope of the line of the graph is going to be your velocity. Now, the slope of line B is greater in magnitude than the slope of line A. Why? Because it's a steeper slope. It's covering more displacement over each unit of time than the line A is. So if the slope of line B is greater in magnitude than A, and slope is velocity, that means the magnitude of velocity of object B is going to be greater than that of object A. What is magnitude of velocity? That's just speed. So the speed of object B is going to be greater than the speed of object A. Okay, part B. What does the intersection of the two graphs mean? Again, remember that this is a position time graph. So the y-axis marks the position of an object. If at a certain time, which is right here, let me choose a different color, right here, the objects are at the same y value, that means they're at the same position. So the intersection of the two graphs means that the two objects are at the same location at the same time. Part D. Does either object turn around? If so, and which one and at what time? Explain. Alright, so recall that an object turning around means that it changes direction. So either from positive to negative or negative to positive. This means that the slope of the graph would have to change too, either from forward slash to backslash or backslash to forward slash. Now, neither of these lines are changing direction. Line B remains positive the whole time and line A remains negative the whole time. So, because the slopes never change sign, the objects are always going to be traveling in the same direction that they started in. So neither object turns around. And I'm going to offer one final reminder that just because the objects change from positive to negative or negative to positive position does not mean that they turn around. And I'm going to quickly show object B's motion to prove this. So it starts at -2 and then goes to 0 and then goes to positive 2 meters. And its motion looks like this. It starts in the negative realm, crosses over the 0 point, and then goes to the positive realm. Not once in its motion did the object turn around like this. It continually went in the positive direction. It was moving in the positive direction all along. So again, object B's starting position, the fact that it started at a negative position does not matter. The only thing that matters is that it's moving in the positive direction. And again, the only way that we can tell an object has turned around on a position time graph is if its slope has changed like this. Okay, example number 3. Part A. Is one object moving at a greater speed, i.e. moving faster than the other? If so, which one is faster and when? Okay, so let's look at the type of graph we have. It's a velocity time graph now, not a position time graph anymore. So to find speed on a velocity time graph, all we do is take the magnitude of the y value of the graph. So, for example, line B over here, it has a speed of 2 meters per second, whereas line A starts with a speed of 1 meter per second. Sorry about that. So, let's see which line has a greater magnitude of y value at what times. Looks like from 0 seconds to 2.5 seconds, line B has a greater magnitude of y value than line A. So it's going to have a greater speed. The speed of B is going to be greater than the speed of A from t equals 0 seconds to t equals 2.5 seconds. But after that, from 2.5 to 3 seconds, in this little section over here, looks like line A has a greater magnitude of y value than line B. So the vice versa is true from t equals 2.5 seconds to t equals 3 seconds. Okay, part B. What does the intersection of the two graphs mean? Well, if we look at this intersection point over here at t equals 2.5 seconds, basically both lines or both objects have the same velocity at the same time. So basically this means at t equals 2.5 seconds, both objects A and B are traveling at the same speed and in the same direction, at least for that specific moment. Okay, part C. Does either object speed up, and if so, which one and at what time? So recall from our graph tips that to find an object speeding up on a velocity time graph, it needs to be moving away from the origin, either in the positive or negative direction, because remember, speed is just magnitude of velocity, so direction doesn't matter. So in this graph, this is only happening at one instance. Starting from t equals 2 seconds, object A is moving away from the origin and gaining positive velocity, or positive speed, So object A is speeding up from t equals 2 seconds to t equals 3 seconds, but that's it. Object B doesn't speed up at all. Part D. Does either object turn around? If so, which one and at what time? Explain. Okay, so recall an object turning around means that its velocity switches direction from positive to negative or negative to positive. And in order to do so, the object has to hit a momentary rest, 0 meters per second, for just an instant in time. So if we look at this graph, there's only one place where a line hits momentary rest, or 0 meters per second, and that's line A. It starts with some negative velocity, then slows down and hits 0 meters per second just for like a moment in time before going positive and speeding up again. So object A does turn around, and it turns around precisely at about maybe 1.9 seconds, or around 2 seconds. And part E. Do the objects move in the same direction at any point in time? If so, when? And if you remember our graph tips, to know which direction an object is going in the velocity time graph, all you do is see whether its velocity is above the x-axis or positive, or below the x-axis or negative. Now, both of our lines are above the x-axis from about 2 seconds to 3 seconds. So, although their slopes are the opposite directions, because line B has negative acceleration and line A has positive acceleration, both objects are still moving in the same direction at that point in time. So from t equals 2 seconds to t equals 3 seconds, the objects do move at the same direction. The only catch is one object is slowing down while the other object is speeding up. Alright, example 4. This is a fun one. In each row below, sketch the missing position or velocity or acceleration time graphs based on the one provided. So here's our first one, and it always helps to describe the motion of an object before you draw the corresponding graphs. So in this position time graph, looks like our object first starts at rest because the position is not changing, before suddenly jumping to a high positive velocity. And so this concept of suddenly jumping velocities, which we did just see in a practice problem recently with a velocity time graph that looked something like this, it's actually not possible in real life. You'd have to accelerate from rest to that high positive velocity. But for the purposes of AP Physics 1, we're going to pretend that it can happen. So we start from rest, and then we jump to suddenly a high positive velocity. And then, as the slope of this curve over here is decreasing gradually, we go like this, and then our velocity becomes like this, until at point D, our velocity is 0 meters per second, because our slope is just a straight horizontal line. So how do we draw this on the velocity time graph? Well, you can draw it one of two ways. College Board likes to draw it by just drawing a straight line and then a line here to show the jump from 0 velocity to this high positive velocity. But if it makes sense to you, you can also add holes here. The velocity starts from 0 and then suddenly jumps up here to this high positive velocity. You can do either works. And then our velocity, because this is a parabolic position time curve, decreases at a constant rate from this high velocity until it reaches zero velocity at point D, which is kind of covered up by my drawing, sorry. And if you're drawing this graph in real life, you should use a ruler to make sure your lines are straight. I don't have access to one in my recording, so this is the best I can do. But if you're drawing in College Board and your line is a little wonky like this, they will take points off. You need to make sure you're drawing with a ruler and have a straight line. Okay, and for our acceleration time graph, we're going to do a similar thing. Since we start at rest first, we're going to have zero acceleration for those first couple of seconds. And then we make a quick jump where we have high positive velocity and we're decreasing gradually at a constant rate because this line is supposed to be straight. So we have a constant negative acceleration. And why is the acceleration negative? Because the slope of this the slope of this line is negative. And the object is slowing down, but in the positive direction. So again, College Board will probably draw it like this, but you can also add holes if that makes sense to you. Okay, example number 5. This time we're given the velocity time graph and we have to draw the other two. So if we look at this graph and describe the motion of the object, it starts at a super high negative velocity and then it slows down until it hits zero velocity, so it comes to rest. Now, in the position time graph, like I've mentioned before in an earlier practice, it doesn't matter at which position you start your graph. What does matter is that your curve needs to move downwards because we're moving in the negative direction. However, like I mentioned before, we're slowing down. So we might start with some super steep velocity slope like this. And then our slope is going to get less and less and less steeper until we have a fully horizontal line. We have a fully horizontal line like this because our velocity has come to zero. So we're going to have a parabolic curve that maybe starts up here and it comes down like this, slope gets less and less steeper until our position just flatlines and it stays the same. And that represents our zero velocity here. Now, let's go to our acceleration graph. If we look at our velocity graph, it should be pretty simple. Our slope of the velocity graph is positive and our velocity line is constant. So we have a constant positive acceleration. And this checks out with what we learned in basic motion. If you have an object that's slowing down, but it's moving in the negative direction, that means its acceleration points to behind it in the positive direction. Okay, and I want to make a quick note about our position time graph real quick. Let's say our axis was stretched out here, so that's kind of negative, that's more positive. Our line could be drawn anywhere. It could be drawn here, it could be drawn down here. It really doesn't matter. Any of these choices are correct. Why? Because again, I want to reinstate, the exact position at which the object starts and ends its motion does not matter. We're looking at how the object moves, not exactly where the object moves to. And so basically the key features you just want to make sure your line has is that, again, it's moving down because it's moving in the negative direction. Second, that it starts with some relatively high slope before it kind of flatlines and then goes to zero slope over here because, again, our object starts with a high negative velocity and then moves to zero velocity. Now, where exactly this line is curved doesn't matter because our position of the object could be starting at a positive position and then going negative. It could be starting at zero. It could already be starting at a negative position and then going more negative. None of that matters as long as it's moving in the negative direction and also its velocity is becoming less. It's slowing down. Okay, example number 6. This one might look a little bit funky, but it's actually pretty simple. So what I recommend we do is break this graph into 2 parts. This first curve over here and this second curve over here. So let's look at that first curve. It looks like this. We start with a pretty flat slope. Let me change the color. We start with a pretty flat slope or pretty low velocity. But then our slope seems to get steeper and steeper. So basically what's happening is that we're gaining speed. And this is happening in the positive direction. How do we know? Because our position is getting higher, but in the positive direction. So our velocity might look something like this. We start at a pretty low velocity and we start gaining velocity. Now, for the second curve, which it looks something like this, our velocity starts off pretty high, pretty steep. Then it starts getting less and less steep until it flatlines at the top. It gets horizontal, which means we have, again, zero velocity or maybe close to zero velocity. So if we want to add that to this graph and see what that looks like, we start off with a super high velocity, but then we slowly start slowing down until we get to a super low velocity. But again, this is still happening in the positive direction. Even though we're slowing down, we're still gaining position. We're still gaining position in the positive direction. So this is still above the x-axis over here. Now for our acceleration though, this is a little bit funky. Because if we look at two parts, we broke the position time graph here, and so we're going to break the velocity time graph over here. This first portion over here has a positive constant slope. So based on previous experience, we'd say our acceleration looks something like this, right? But the second half over here has a constant negative slope. So again, based on our previous work, we'd say our acceleration looks something like this. So this is the same thing, the same concept we saw earlier with velocity. Our velocity suddenly changed from low to high or high to low instantaneously. So again, this can't really happen in real life. This acceleration can't go instantaneously from positive to negative. But in AP Physics 1, we're pretending it can. So again, College Board usually draws acceleration or an instantaneous change in velocity or acceleration like this, but you can also add holes if that makes sense to you. Alright, example number 6. Which object has a greater magnitude of acceleration and which object covers a greater amount of displacement? Now, this example might seem pretty simple, but you'd be surprised how it might trick some people. So for the greater magnitude of acceleration, remember that acceleration is the slope of a VT graph, which is what we have over here. The slope of the graph for object A is 0. This is a horizontal line. The velocity is not changing. It's constant. Whereas the slope for object B is non-zero. This is a linear graph. It's a backslash, so it does have some negative acceleration. So the magnitude of acceleration is greater for object B than it is for object A. Now, which object covers a greater amount of displacement? Recall that for a VT graph, the displacement is the area under the curve of the graph, or the area between the line of the graph and the x-axis. So that's this area right here and this area right here. Well, you might be saying, oh, I don't know, I can't tell because this area added together might probably be greater than object A or could be equal, I'm not sure. But the key thing you have to remember is that the area under a curve that's below the x-axis, so this area right here, is negative displacement. Not positive, negative. So because these two sections look pretty equal, if not the same in size, object B's displacement covered is going to be close to 0 or 0, whereas object A's displacement covered is going to be some positive number that's greater than 0. So object A covers a greater amount of displacement than object B does. And I wanted to make just a quick note that you guys should be comfortable doing approximations like we did here in this problem, because again, in the AP test, it's less about exact calculations and more about understanding ideas behind problems. Like for example here, that object B travels close to 0 or 0 displacement. So just make sure that you guys don't feel iffy about approximating. That's totally okay. Alright, you have reached the end of our graphs lesson, and I want to give a super quick tip or piece of advice. Those little graph properties or tips we had at the end of each different type of graph section, we use those so much in our practice problems. So those are super duper helpful to know. Like for example, on a velocity time graph, if you're moving closer to the origin, you're slowing down, or on a position time graph, if your slope is positive, you're moving in the positive direction, things like that. You won't have time on the AP Physics exam to look at a graph and sit and deliberate and figure out that kind of information. You want to know those things like the back of your hand. So I suggest going over graphs, different types of graphs, and seeing if you can remember the different types of information you can glean from each type of graph. It's super duper important, and it'll help you so much on the AP test if you just know those facts off the top of your head. So yeah, our next time lesson is going to be kinematics equations, so keep an eye out for that, and see you later. Bye!